Hello, Algebra I students. This is Mr. Kraft coming to you from my house. I hope you had a great spring break, that it was enjoyable, and I hope you had a wonderful and blessed and holy Easter. I hope everyone has had some time to rest and have time for recreation and so forth in whatever way. And I hope you're all ready for classes starting back tomorrow. Even though we will not be meeting in person, we are back to doing classes online. So this is to fit in with your written assignment or your assignment that's posted on Google anyway. I'm not giving you anything to write for any problems for tomorrow, although I will be doing so on Tuesday. I'm giving you a slight break to start getting back into the swing of things. I assigned you a section to read on scientific notation, and so that's what I want to talk about in this video. In science, we often deal with very, very big and very, very small numbers. So, for example, closest star to our own, to us rather, aside from our own star, the sun, is called Proxima Centauri. And in miles, it is about 25 trillion miles away from us, which is quite a long distance. On the other hand, if you take something like an electron, as you probably know, an electron, you have an atom. The atom is made up, the middle of it is a nucleus. It's made up of particles called protons and neutrons. And the electrons orbit it. Orbit is not quite exactly the right word to use, but that gets into some deep physics, which I won't talk about here. An electron is very small. Uh, it is about that much of a kilogram, which is tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, billions, 10 billions, 100 billions, trillions, 10 trillions, 100 trillions, quadrillions, 10 quadrillions, 100 quadrillions, quintillions, 10 quintillions, 100 quintillions, sextillions, 10 sextillions, 100 sextillions, septillions, 10 septillions, 100 septillions, tillionths, 10 octillions, 100 octillions, nonillionths, 10 nonillionths. So 3 10 nonillionths of a kilogram, which is very, 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 very small. Obviously, when you are writing extremely large numbers like this or extremely small numbers like that, you get lots of zeros very rapidly, and that's a problem. Unfortunately, science on a regular basis deals with numbers that are very large or very small, thus just like that. So the question is, how do we write those numbers conveniently? And that's where scientific notation comes into play. So you remember years ago when you were learning your numbers, you have place value. You have your ones place and your tens place and your hundreds place, thousands, 10,000s, etc., etc., etc. We'll come back to that in a minute. Let's take powers of 10. 10 is equal to 10 to the first. As we talked about in exponents earlier, any number to the first power is just itself. Actually, I should probably reverse the order in which I show those for various reasons. 10 to the first equals 10 by definition. 10 squared means 10 times itself, which is 100. 10 times 10 is 100. 10 cubed equals 10 times itself 3 times. 10 times 10 times 10, 1,000. I'm not going to write all the multiplication out from this point. 10 to the fourth, 10,000. 10 to the fifth is 100,000. 10 to the sixth is a million, and so on. One thing you might notice is interesting here is that every single one of these powers ends up with the same number of zeros as the exponent. 10 to the first is 1, 0. 10 squared is 1, 0, 0. 10 cubed is 1, 0, 0, 0. 10 to the sixth is 1, 0, 0, 0, 0, 0, 0. And so that gives us kind of a handle on an easier way that we can write very, very large or very, very small numbers. So let's suppose I had something like this. Start with a simple case. Big but simple. 10 trillion. Only halfway to, in numbers, that's only half of the distance to the nearest star, not even as much as that. The nearest star, like I said, is about 25 trillion miles from us, the nearest star besides our own. Give you an idea of how far away from us that is. If the spaceship going the fastest that any spaceship has ever gone, the fastest any spaceship has ever gone was the Apollo 13 craft. Briefly, during its re-entry, it briefly reached a speed of 25,000 miles per hour. That is so fast that at that speed you could go clear around the Earth and back and more in an hour. At that speed, it would take 100,000 years to get to the nearest star besides our own. This is half of that, so it would only be 50,000 years. Still a very big number. Anyway, we said that with powers of 10, the number of zeros, 3, 6, 9, 12, 13, is the same as the power. So I could rewrite a number like 10 trillion as 10 to the 13th power. Well, what if it were 20 trillion? 3, 6, 9, 12, 13. Well, that would be 2 times 10 trillion, or 2 times 10 to the 13th. This is the kicker. This is the key to scientific notation. We take a number, we change it so that it's something times some power of 10, or a multiple of 10. And that power of 10 we rewrite in exponent notation. I wrote 13. I meant 13 as a 3 instead of 13. Anyway, so instead of having 13 zeros, we have just 1. Instead of saying 1, 0, 0, 0, so forth, we write it as 10 to the 13th power. So 20 trillion would just be 2 times 10 to the 13th power. If I had 3 units, thousands, millions, billions, trillions, quadrillions, 30 quintillion. We have 3, 6, 9, 12, 15, 18, 19 zeros. So 3 times 10 to the 19th. I'm skipping those extra steps. So with a very large number that's just one single non-zero digit followed by a bunch of zeros, the non-zero digit times 10 to the 19th power, or 10 to whatever the number of zeros is. All right. What about very small numbers? What about very small numbers? Like you have something like this. Tens, hundreds, thousands, 10,000s, 100,000s, millions, 10 millions, 100 millions, 5 over a billion. So what that would be, it would be 5 over 1 billion. 5 billionths. 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 Not billions. Billionths. How do you write that? Well, let me remind you of something we talked about in exponents. I may put up a separate video to go over this. I think we touched on it before, but let's touch on it again. A number to a power means times itself that many times. So 2 cubed means 2 times 2 times 2. A number to a negative power. A negative number does not, a negative number on the exponent rather, does not make this number negative. This number is still positive. What a negative exponent means is a reciprocal, fraction. So 2 to the negative third means 1 over 2 to the third, which is 1 over 2 times 2 times 2, 1 over 8. Right. So what we're concerned about here is how do you write very small numbers as exponents? So we'll get to this one here in a minute. Let's do a very simple example. 0.03. Tenths, hundredths. Remember, this zero here is just a filler. You may omit it, but I'd rather you didn't. If you do insist on omitting it, then make your decimal nice and dark so I can see it. That's better. Don't count that into the place. Tenths, hundredths. Well, we said earlier that powers of 10, the power is reflected in the number of zeros. Let's do it the other way. 1 over 10 as a decimal is 0.1. That is 10 to the negative 1. So not counting your filler zero, you actually have one place to the left of the number. There's no zeros. 1 over 100 is tenths hundredths. That's 10 to the negative 2. 1 0. Thousandths. Tenths, hundredths, thousandths. So we got negative 3, 2 0, negative 2, 1 0. So it's a little bit different in that respect from the way it is with whole numbers. So essentially what you're doing is if you had 300, you'd say that's 3 times 10 to the 2 zeros 2. This is a little bit different. 3 times 10 to the negative. 10's exponent will always be negative when you have a decimal. In this case, it's still going to be negative 2. 100 is positive 200th, negative 2. But in this case, large number, the exponent and the number of zeros is the same. With a decimal, the exponent is always one more than the number of zeros. That makes sense? So, what is 5 over a billion? 5 times 10 to the negative. Well, 1, 2, 3, 4, 8. It's going to have to be one more than that. 5 times 10 to the negative 9. Okay, I hope that's reasonably clear. By the way, Cal has a Zoom account. I've not been given the password for it yet. As soon as I get it, I'm going to get hold of everybody. The Zoom has a whiteboard function on it where we can not only see each other virtually face to face through the computer, but I can do this whiteboard stuff as we talk. So if you had a question or something, I could put it up right when you ask me, just exactly in real time as if we were in a actual classroom, but through the computer. So anyway, what happens when you have something like this? I said 3,000 equals 3 times 10 cubed. Well, that's fine and dandy. We said count the number of zeros, and that gives you your place. What if we had 3, 5, 2, 0? Well, if I were going to go by the same rule that I did before, I would say, well, 352 times 10 to the first. Not how we do it. So that's not even going to happen. The rule is this. Go back to what I had. 3520. What you do is you take the non-zero portion of your number and you put a decimal after the first digit. Always, always, always put a decimal after the first digit. If you don't have a decimal after the first digit, it's not right. Times 10 to the. Now, instead of counting zeros, you count places. Always start after that first digit. 1, 2, 3. And as you would expect, you're dealing with thousands in both of these cases. You get it times 10 to the 3. So if you would have had 3527, it would have been 3.527 times 10 cubed. You would have had just 3,500. That would have been 3.5 times 10 to the third. So you're always counting the number of places from the decimal. And the decimal is always after the first digit of the non-zero part. Sometimes we call the non-zero part by a fancy name, mantissa. Um, it's a technical word, but you'll see it again when you get to pre-calculus, possibly algebra 2, and definitely physics. And, it doesn't hurt to learn the terminology. So if I say mantissa, that's just a quick way of saying the non-zero part. So let's go back to something I showed you just a few minutes ago. So we said the distance to Proxima Centauri, the nearest star to ours, 25 trillion miles approximately, about 100,000 year-long trip at any speed that we've ever attained so far. So what do? We look at the mantissa and we put that decimal after the first digit. Not here, not there, after the first. Count places. 3, 6, 9, 12, and counting the 5, 13, times 10 to the 13th power. Much nicer that way, doesn't it? The mass of the Earth is about, I think that's the right number, but I'm just going to go wild and crazy here and not look it up. Kilogram. I said the weight of the Earth, mass of the Earth, really. Mass and weight are not quite exactly the same thing. We say kilograms are the metric unit of weight. They're not. But that's a discussion when you all eventually take physics, those of you who do that. So, the mass of the Earth. Once more, take that mantissa, that non zero part, decimal after the first part. 1, 2. Then 3, 6, 9, 12, 15, 18, 21. So with times 21, 22, 23, 10 to the 23rd power kilo. So that's another example of how you write a very, 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 very large number. What about very, 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 very teeny numbers? Well, you do the same thing, but in reverse. I had 0.000007 tens, hundreds, thousands, 10,000s, 100,000s, million. 7 times 10 to the negative. The easiest way to do it, you could say count the zeros and add one more number to it. The way I say is start to the right and then go to the left. To the left, as Beyonce would say. Never knew she was thinking about decimal numbers with scientific notation, did you? So, 1, 2, 3, 4, 5, 6, which is 2, 3, 4, 5, one more of the number of zeros. If you had, I don't know, something like this, once more, take that mantissa, slap a decimal after the first digit, times 10 to the negative, 1, 2, 3. Easy as that. So that figure I gave you for the weight, rather the mass of an electron, I'm not going to write the number out again. It was basically 9 times 10 to the negative 31st kilogram, which is even smaller than the Earth is big. So that's how you write a number like that. Okay, so the typical types of questions you have when you start off are questions like this. Typical questions you will get are convert from standard to scientific notation. Then you'll get asked to do the opposite, scientific to standard. Well, standard to scientific, what do? Take that mantissa, non-zero part, put a decimal after it, after the first digit, times 10 to the, then count. That first decimal place forward to the right. 1, 2, 3, 4, 5, 6, 7. That's it. For a decimal, you do the same thing. Get your mantissa and put the decimal after the first part. 1, 2, 3, 4, 5 plus 1, and it's negative, or you can just count the places to the right of the 4. 1, 2, 3, 4, 5, 6. Remember, You never count that guy. Put it there, please, because it makes it look much nicer. And if you're the type of person that makes a little decimal point, see there, that you can barely see, it makes it easier for me to read it and grade it. But please, please, please do not count this guy into that total. So you're not counting it for the purposes of what we're talking about. Okay, to go the other way, scientific standard notation, you write your mantissa down, you leave out the decimal, but you go where the decimal would have been, and including any numbers, you put your zeros in. 1, that leaves me 7 places. 2, 3, 4, 5, 6, 7. Then from your right, you go to the left again and put a comma every 3 places. 9.6 times 10 to the 8th power is the same thing as 96 million. Decimals are a little bit easier because you never have to count these guys. You're always going to end up one less in the exponent. 1, 2, 3, 4, 5, decimal, filler 0. So I guess if you count the filler 0, you would have the same number, but that's not a good way to memorize it. Okay, that is a summary of how scientific notation works. And tomorrow expect some very simple questions or lesson opener or written work about this. It should not be too difficult. I hope once more that you've had a good time off, and I hope you're in a state of mind ready to jump back into things. And I will talk to you later. Bye.